To the 7th installation of our 10-month climate change speaker series. Today's event is going to focus on agriculture, impacts that we are looking at with regard to Washington's agricultural sector, as well as policy implications, both from existing policy landscape as well as what we can expect in the future. We have two guests, one from WSU, Chad Kruger, who's the interim director of the Center for Sustaining Ag and Natural Resources, and Kirk Cook is joining us from Washington State Department of Agriculture, who is their climate change lead. So I also want to point out that out in the hall today, a couple months ago, we had a Reduce Your Footprint session, and so I'm going to introduce Ramsey from Thurston Energy to talk about what they're doing out in the hall, if you want to check it out when we're finished.
Thank you. Thanks a lot. We're with Thurston Energy. We're a joint program with the Thurston EDC, Economic Development Council, and the Thurston Climate Action Team. But what we do is home energy assessments, and then once we can get into your house and help you to understand the ways that your house uses energy, we can then help you to find contractors to do work or learn how to do it yourself. We can connect you with tax incentives and rebates and discounts and all kinds of things like that. So if you want to stop by and talk to us, we would be very happy to set that up for you.
Thank you. And they will be outside through the duration of this and also afterwards. So without further ado, here's Chad.
Okay, so I'm going to talk with you about some of the research we've been doing at WSU. A good chunk of this is part of the UW-SIG's Washington Assessment, or Washington Climate Change Assessment, Integrated Assessment Project. And then I'm going to talk about some other stuff that we're doing right now. So, just the first comment is there's a whole lot more yet that we're not able to assess in terms of potential impacts of climate change on ag. So a lot of what I'm going to present is the stuff that we can do some fairly good predictive modeling on. But when you look at that, Centralia Valley, farms wiped out in that case. That's pretty hard to predict in terms of impacts, how often that's going to happen, as well as what is an adaptation strategy other than get the cows out of the valley kind of thing. I'm going to start with kind of a U.S. perspective. These are a couple of different climate change scenarios, and this is a corn model. This actually, I don't want to talk too much about the methodology, but it was done on a county basis using economic data, historical data to project. If we see increases in temperature, what's the likely impact on corn production across the U.S.? Basically, everywhere it's dark, it's getting, yields are going to go down, are predicted to go down based on climate change scenarios. So you can see in the more serious scenarios, and I can't remember what the dates are. What's the date? I think it's 2080. You can see that yields are going to go significantly down in corn production in the U.S. We've seen in the literature globally that this total global food production predicted to decline under a climate change scenario. Now, all models are wrong, some are used. The work that we've done is based on models, so predictive tools, mechanistic models, not statistical models, but we actually have a model that says we're going to grow the plant under the conditions that are stated in the data sets that we got from the UW, and say if temperatures increase, if precipitation changes, what's going to happen in terms of biomass productivity on that plant. There's some things that we can't do very well yet, things like quality. So I'm going to show you some data on potatoes. Well, we know that yields on potatoes are likely to do one thing, but we can't tell you what tuber quality will look like. Same thing on a lot of the fruits that we grow. We can predict generally based on assigning a certain part of biomass production to yield, but if you got hit with the frost at the wrong time, it could wipe the quality of the crop out. So, go ahead. So just a reminder, the WSDA assessment, basically downscaled resolution of the global climate data for our region, kind of 6-kilometer blocks, and then we applied case studies where we actually ran agricultural models to predict what would happen under those changes. Just a sense of what we're looking at when we talk about the Pacific Northwest and agriculture. We've got another project that we actually just found out last week. We're a finalist for a $20 million USDA proposal. So we spent all morning this morning planning for our trip back in 2 weeks to defend that proposal. But the concept here is there's a lot of heterogeneity in the Pacific Northwest, meaning a lot of people think about the very little bit of agriculture we have on the west side, but the majority of agriculture, at least in the inland Pacific Northwest, ranges from really dry land production where it gets so dry that the only way you can grow anything is to irrigate it, all the way up to really wet out on the Camas prairies in Idaho. And this is just, we've kind of divided it out where we've got the irrigated region and then grain fallow where you can only get one crop every other year, annual crop dry, which is basically 2 crops in 3 years, annual crop wet, all the way on up to where there really are a fairly robust system from a moisture standpoint. So moisture is a key driver in our state. The other side of this is the temperature side. So that doesn't show up really well on that screen. But basically, it's really hot right here. And I'll show you some data sets later that show not only do we have a problem in terms of how much moisture we get, but we run out of that moisture really quickly in a lot of our systems because of how hot and dry it is during the growing season. Our case study sites kind of run the gamut, at least in Washington State, across that gradient. And so we have 2 irrigated sites that we looked at, Sunnyside and Othello, and we have 3 basic dryland sites, and I don't even remember why we have Odessa on there, but a low rainfall, medium rainfall, and high rainfall sites where we actually ran case study simulations, and this will come back. So just a reminder of kind of what's been predicted, because I know that you've heard this before. Temperatures are expected to increase. Precipitation is expected to increase too. But basically, we're looking in kind of these windows. We did all 3 of 2020s, 2040s, 2080s. When you really look at it, 2020s isn't that far from now. So you're not going to see a lot of change between now and then. 2040s, we're going to start to see some interesting questions. Of course, 2080s, all hell could break loose, but that's really hard to predict what the impacts are. So kind of the first thing I wanted to show you was changes in frost-free days. And 2020s, 2040s, 2080s, the lighter it is, the change in direction, the more frost-free days that we will have. So the longer technically the growing season would be, with the exception of you got to have moisture to get use from that. So you can just kind of see it's fairly significant. There was another paper that was published that indicated nationwide the average in change of frost-free days would be over a month by the end of the century. Okay, so now the annual and seasonal mean temperatures for some of our sites. And Pullman and Sunnyside, those are kind of the 2 extremes, so that's what we've got here to show. Annuals on top, seasonals on the bottom. You can see the trend is we're going to get warmer at both places. In season, we're going to get warmer. Okay, so now looking at changes in precipitation. Here, because the historical record is so highly variable, it's really difficult for the modelers to model what likely changes we'll see in precipitation. So they think that we're going to see a general increase in precipitation, but there's an awful lot of variance in what they're predicting. So they're just not really confident in that. So from an agricultural standpoint, what matters is soil moisture profile, how much moisture is actually in the soil when you need it. So annual precipitation and evapotranspiration potential. So precip on the left bar in every one of these cases, evapotranspiration, or PET, on the right. So Pullman, Sunnyside. On an annual basis, we get a lot less precipitation than we have potential for evapotranspiration. So we're a dry system. We're a moisture-limited system. That's why we don't grow trees. Seasonal, it starts to look even worse, that trend. So because we get most of our moisture in the winter, plants grow in the summer, we tend to run out of moisture when we're trying to grow our crop, and that's our barrier to increased crop growth. So you can see if we can fill that gap with irrigation in Sunnyside, that's why we can yield so much better under irrigation than under dryland conditions. And actually, go back to that. Even thinking about Pullman, which we think of, I actually live more in central Washington, we think of Pullman as really wet from an agricultural standpoint or dryland production standpoint. In our state, it's about as wet as you get, other than the west side. And yet still, you know, there's this huge gap. So, okay. There's another factor that we have to consider, and I don't know if anybody else that's presented to you has talked about this, but we don't just consider temperature and precipitation changes, but we have to consider this, what they call the CO2 fertilization effect. And who's heard of this? I'm sure some of you have. Most of the experimental studies that have been done on CO2 fertilization have been done in natural systems that are nutrient constrained. When we've done this work in terms of our looking at it from an agricultural standpoint, we're not nutrient constrained because we're going to assume that we've supplied enough nutrients for plant growth under the conditions of water that we have. And the result is kind of interesting, that CO2 actually has a fairly dramatic fertilization effect on our managed plants. And it's more important for the C3 crops that we grow here than it is for corn. So I showed you earlier that corn model that said things are going to get worse. The CO2 fertilization effect is not predicted to have that great of an effect helping corn under a climate change scenario, simply because corn's a C4 photosynthetic pathway, and it's just already evolved to the point where it's fairly efficient in its use of water to produce biomass. Whereas wheat is just the opposite. Wheat will actually get a greater increase relative to the amount of water that it has with additional CO2 fertilization. So that's going to come back into play. So here's some of the results. And basically what we did is we grew the plant. And so this is winter wheat, and these are the 3 dryland sites, the low, medium, and high rainfall. And 2020s, 2040s, 2080s, basically this is, we just ran the model without ever calculating in that potential CO2 benefit. And what you see is we're going to get a slight increase in production. Of course, everything's relative to 1. And then over time, we're going to see a reduction. In Lind, we're actually going to see a slight increase in total yield. And in St. John, kind of a mixed bag. But then when we add that CO2 fertilization effect, this projects out that we're going to be fairly okay, because that CO2 fertilization effect will likely overcome limitations of soil moisture, because we'll be more efficient in using the moisture that we have. So go ahead. Next one is spring wheat, and you notice we only have 2. We pulled the Lind study out because we can't grow spring wheat very often in Lind because there just isn't enough rainfall to get it out of the ground. And so we've got a couple things. The first 2 bars are the same ones I just showed you. So yield is on spring wheat is predicted to decline fairly significantly under a climate change scenario, largely because we dry out quicker. So St. John's going to look a whole lot more like Lind in the 2020s, and Pullman's going to look a whole lot more like St. John or in the 2080s. But then we calculate that CO2 factor in, and again, we kind of mitigated that change in soil moisture. But then we said, well, and I know this is the part that we've done that nobody else in the SIG report did, because the way that we think about our models isn't just, this is what could happen. We think about our models from this management standpoint. What can we actually do to mitigate the problems that we're going to see? And so we said, well, what if we took that spring wheat? It's 2 weeks earlier, it's going to be warm enough to plant, so why don't we just move it back and plant it 2 weeks earlier? Makes some sense, right? So by moving back and planting 2 weeks earlier, and also considering the CO2 effect, even spring wheat, except for way out in St. John, we can actually probably mitigate or adapt to climate change scenario in production of this crop. Now I'm going to move to the more complicated things, fruits and vegetables. fruits and vegetables drive agriculture in this state. We like to think about the big wheat belt, and more acres are planted to wheat than any other crop. And yet the value, the real value, is here. So these are the big driver crops in the Columbia Basin and all our central river valleys. So we did kind of the same thing. This first bar is what would happen without any consideration for CO2. The second bar is with the CO2 effect. So apple production without CO2, pretty close, but with CO2 fertilization could increase. Potatoes, without CO2, it's going to take a drop, but with CO2, it's going to be pretty close. So that looks pretty good. But again, I said, this is just yield, or an interpretation of yield based on carving off a certain percentage of biomass as yield. This doesn't say that those two are going to be any good. So instead of maybe getting big potatoes, you get little tiny potatoes that you can't market. We don't know those kinds of things.
And adaptations that genetically altered crops?
Yeah, I'm going to talk about that.
And I forgot to say at the beginning, let's try and hold all of our questions to the end, that we can have a big discussion.
So with potatoes, we could technically plant 2 weeks earlier. With apples, you can't really plant 2 weeks earlier. So we actually, for both of these, we came up with a different theoretical adaptation. And that is, we know we've got another 2 weeks of growing season. So what if we had a plant that was green for 2 weeks longer? The genetic material that we have that we work with right now is green for a certain period of time. So 2 weeks of additional green leaf area, in theory, should adapt to, or enable us to adapt to that. And lo and behold, if we can do that, we should be pretty good in terms of yield again. Now, that adaptation does not exist yet. So that's one where, going to the work you're doing, that's one where we've got breeding issues. It's genetic development. Okay, so that was kind of yield. Now I'm going to shift a little bit to pests, because pests probably are the bigger concern. So we feel pretty good about what we've done on yield. We know there's some questions around quality and development of the plant that probably need a lot greater investigation. The pests, we know this is an issue that we're going to deal with. So the concept here, and we use codling moth as the case study because it's the most important economic pest for tree fruit. And basically we have 2 complete generations per year now. The question is, how often are we going to get that 3rd generation of codling moth? Because we have a longer season, we have more overwinter survival rate. So codling moth is currently 2. What about another pest that already has 15 generations? You can go on out. So go ahead and flip. So when we looked at codling moth, this is kind of a busy slide. There's a couple things going on here. This is, for the first 3, is day of the year. For this last one, it's a percentage basis. So the first flight happens on about the 112th, 113th day of the year now, and you can see that as you go forward, it's going to happen sooner. The first generation peaks here, and sooner or later it's going to get sooner. Or, as you go on, it will get earlier in the year. Second generation, kind of the same story. And then this last one is probably the big telling factor. The fraction of the 3rd generation that will hatch on average, goes from, fairly small right now to, by the 2080s, we pretty much are going to have a 3rd generation of codling moth. And again, I said, this is a, fairly long life cycle, 2 generations currently. What about the pests that have 15 right now? But what's the implication there? The implication there is we have to get smarter about management. We're probably going to end up managing 1 more generation, whatever that means. That may mean more insecticides. That may mean different strategies for management. But we know it's going to cost us more regardless of what we do. And if it does mean more insecticides, we've been trying to transfer our entire industry from the harder organophosphates to softer pesticides. Well, those pesticides, we know that every time you use them, they're on a trend to becoming less efficacious. So the more use in a year, we have a shorter window. We're going to need some new strategies, whether that's new chemistries or new management strategies to deal with those. Now, going to diseases, and this is a little bit more of a mixed bag. And so we looked at powdery mildew on grapes and cherries, and this is the average number of days of the risk. So the risk is either low, medium, or high. So historically, low, medium, high in terms of average number of days. And it's interesting, as you look at powdery mildews on grapes, low and medium risk days actually go down, but the high risk days go up. And same thing on cherries, only the high risk days really grow. So, and there's been some other things that, because of disease, unlike a pest, which is a degree day driven issue, where the more degree days you have, the more pests you're going to have. The diseases are not. They're degree day driven, but they're also driven by several other factors, and it can be a window. So it can be 1 or 2 degrees at the right time, and you'll have a powdery mildew outbreak. 1 or 2 degrees lower or higher, and you won't. So it's more of a mixed bag with the diseases that in some cases we may have more problem, in some cases we may have less problem. And it's an indicative that we probably need to be looking at that a lot closer. Okay, so now I'm going to shift from kind of the obvious production issues to the other really fundamental issue, and that is water. So we already know that we're a water-limited system. And I know you've seen all of this stuff, so I'm not going to belabor it, but go ahead and flip through this slide. We know that we use the Cascade Mountains as our reservoir for water for irrigation, as well as everything else. Looking at the Yakima, the historic simulation, this is the flow of water. Well, wait a second. Can't see it. This is the flow of water. And 2020s, 2040s, 2080s. So we're going to see, we already have problems with enough water in the Yakima. There's several other of our basins that have issues. And we're going to see more of that water moving towards the winter in terms of its runoff. You all know this problem. Agriculture is right at the heart of this problem because I think agriculture uses 80% of the consumable water in this state. So this is big. Go one more. But the results of that are not completely intuitive either. So this, Mike Scott at P&L has done this. We're trying to look at what will the impact of those potential water losses have on actual production and actual farms. Basically, he's divided between those with senior water rights and those with junior water rights. Senior water rights are the ones who pretty much get their water every year no matter what. It'd be a pretty crazy year if they didn't get them. Junior water rights are the ones that get prorationed. And so we've got without CO2 and with CO2 again, 2 different scenarios, 2020s, 2040s, 2080s. And you can kind of see that as we get out into the 2080s, we do see significant yield reductions for the junior irrigators, much more so than the senior irrigators. So what does that mean from a management standpoint? Well, the number one answer that everybody wants is, let's figure out how to store more water. But, from another management standpoint, that may mean that these guys probably shouldn't be growing apples. They probably should be moving to a crop that has a lot more resiliency, that when you get cut off every other year, you don't lose your entire investment. And we see some of that going on already, but that has an impact in terms of, value of land, economics of that production system. Okay, so one last thing I'm going to very quickly talk about. You've seen the SIG stuff. We're actually going one step deeper, looking at the entire Columbia Basin, focused specifically on the state of Washington for the Ecology's Office of the Columbia River. We're actually doing an assessment of water supply and demand. Our role, our big part of that role is actually the ag part of that role. We're doing the hydrology and the ag part. We're working with DFW on fish issues and other stuff we're basically pulling from literature. But we're trying to help them increase the power of the tools that they have to do this supply and demand forecast. Go ahead. And so the concepts here are create baseline forecasts for agricultural production in 2030, model economic focus scenarios looking at changes relative to that baseline, and then take that information and incorporate it with our physical models, both our cropping system model, CropSyst, as well as VIC, which is a hydrological model from UW, to look at how those changes could affect supply and demand of water. So for instance, you've seen some of the work that I just presented that said yields could go up if there's enough water. We assume in those studies that there would be enough water. But if there's not enough water, yields won't go up. And there's also the whole interplay between, the non-consumptive aspects of water use and the consumptive. Well, VIC has it has a vegetation submodel in it that tries to predict what happens with water flowing through the subsurface. We're actually replacing that with CropSyst. So we're saying, instead of looking at just generically whatever vegetation category, let's look at wheat, let's look at apples, let's look at 18 different crops, because they use water differently. These are managed crops. These are genetically adapted crops. They're not, strictly just vegetation. In many cases, they actually use water more efficiently, or use more of it, so less of it actually flows back. So there could actually be some significant things. We're about halfway through that project right now. And the other thing is, you can't do all that modeling in the absence of thinking about what are the larger factors at play. So what if wheat production worldwide tanks, and wheat production here in this state becomes that much more important to feed the world? Those kinds of questions, those are economic questions. And so we've got a number of scenarios that are economic scenarios that are designed to predict different types of things that could happen globally that would affect our crop choices here. What happens if one of our primary, let's say wine grapes, just gets completely wiped out by a pest and we can't grow wine grapes? What would happen? So we've got several different kind of refined scenarios that are designed to capture many of these different potential things, and basically looking at how would those affect the crop mix, because that crop mix can be fairly significant in terms of its water demand. And so this is actually something hasn't been done before, combining all those different things into a single. It's a process model. It's not an optimization model, but it should be very interesting in the results of it. So I'm going to conclude with this statement from Stella Coakley, who's one of the deans at OSU's College of Ag. So climate change will add another layer of complexity and uncertainty onto a system that is already exceedingly difficult to manage on a sustainable basis. Agriculture is the business of managing climate to produce crops, and it's just going to get more complicated. So, I think one more slide. And here's some of the additional research, so you can read our report along with everybody else's stuff there. So,
thank you so much, Chad. And up next we have Kirk Cook from Department of Agriculture, and we're going to shift gears a bit and talk about policy. So when he's through, we should have a nice integrated discussion.
Well, let's hope. Yeah, Chad, that was a great presentation. Chad and I have kind of been tag teaming over the last few years on these things. He's definitely more the expert on all the research stuff, and although I may not say I'm not big of an expert on policy, I've been taking a lot of what Chad has been doing at WSU, has been doing this Center for Sustainable Agriculture, and working it into different policy positions and moving that forward into our involvement in the preparation and adaptation group, and involved with input into legislation for things like carbon credits and carbon offsets and stuff. So I kind of want to take this conversation and talk a few slides about the global issues and then reduce it down to the regional issues. You touched on a couple things just before you ended your talk, and that when you talk about climate change and policy decisions related to climate change in agriculture, we look at both, and we have and will continue to look at both the adaptation part and the mitigation part. Because so much of Washington's agriculture is tied to the global economy, it's very hard for us just to make policy decisions based solely on regional type effects, because global effects have a lot to do with decisions that farmers will make as to what crop they're going to grow, when the growing season starts, what kind of chemicals or agricultural tools may be used based on what's accepted by other countries and so forth. So overlaying everything that we do from a policy standpoint related to climate change in Washington is keeping in mind global exports and what currently is the case now and what will happen in the future. And some of the things that we are aware of is that based on the climate models that are currently existing out there, we in the Pacific Northwest from an agricultural standpoint are probably in pretty good shape as compared to some of the other parts of the country. We'll go to the next slide here. This is a map from the United Nations, and it shows, based on unmitigated carbon emissions, what crop yields are predicted to be in the 2080s. And the colors didn't come out right, but all these areas here in the dark purple are, generally speaking, looking at declining crop yields. And then we come up here and we look at the Pacific Northwest and Canada here. We have, at least up to the 2080s, generally speaking, increases in crop yields. Well, what that says to us is that there is going to likely be more pressure on our growers in this part of the country to produce crops and increase yields to make up for the deficits that are going to be happening across the rest of the world. Next slide. So we think about that and the decisions and the policy considerations that we're making. We first focus on regional, but we can't help but also factor in global economics and how that may overlay what the ultimate decisions may be by our growers. So it may be, it may seem based on the information that Chad has that, yeah, okay, it would make more sense for us maybe to decrease apple production. However, if we have enough global demand, that may force counteracting of that and then cause a shift in the management priorities. It's easy to say, okay, well, if we don't have this amount of water, then we're not going to grow these apples. But if the demand is sufficient enough, then there's going to be inertia to overcome that, the decreases in availability of water because we've got such a high value for this crop and such a pent-up demand from a global standpoint. So you're as much as when you're looking at policy, you're as much as a hydrologist, a crop scientist, and an economist in trying to figure out, a good holistic standpoint from a policy standpoint related to climate change and agriculture. Like I said, Pacific Northwest is probably going to fare better than most parts of the world. Demand for stable and high-value crops will likely increase, which means there'll probably be more pressure for increasing the crop yields for our growers in this part of the country. And we need to think about what actions need to be taken to promote both climate change and the economic reality. So it's a real balancing act here. Okay, the big one for agriculture and where we are looking at as far as putting a lot of effort right now is the issue of water. When Chad came up and gave his remarks and you read the SIG report, and you look at a lot of other reports predicting what the impacts are going to be to agriculture related to climate change in this part of the country, there's always the caveat, provided there's enough water. And so from a state standpoint, we are heavily involved with Department of Ecology, Fish and Wildlife, DNR, in looking at the preparation and adaptation mechanisms that we're going to need to employ to make sure that there is an adequate supply of water. And when we talk about adequate supply, obviously our main concern from WSDA is adequate supply for agriculture. But we also have to look at who are the users of the other pieces of the pie. So we also have to consider urban uses, industrial uses, and things like that. Having been involved in the 2007 reports related to climate change, and then again involved in the preparation and adaptation process that's going on, the issue of water from a policy standpoint is a multi-pronged question. Storage alone is not going to take care of it. Conservation alone is not going to take care of it. Delivery efficiencies is not going to get us to where we need to be. Neither just changing what we do with land use. It all has to be wrapped up into one. And it's a very fluid model. Sometimes that you can imagine a piece of the pie where the slices are continually shifting depending on what the current data that we have to look at. But comprehensive water management planning is where a lot of policy efforts are going into now. We have representatives on the Yakima Basin Water Enhancement Group, which is more or less serving as a bit of a model on how to take into consideration all the water users within a basin and all the political nuances involved with that, and still make sure that there is sufficient water available for all the water users. Next slide, please. From a mitigation standpoint, we have been heavily involved in working with the Department of Ecology on developing markets for things like carbon offsets and carbon credits. We have been working with ecology and commenting back for the federal legislation, some of the cap and trade legislation, and also working with WSU to help quantify exactly what may be our market here for our farmers as far as carbon offsets. Right now, there's probably a higher likelihood that we're talking about some sort of carbon credits available to growers than offsets. Now, why are we so interested in the promotion of carbon credits and carbon offsets? Anybody who has any knowledge about potential for agricultural offsets or credits knows that nobody is going to go into the business of farming carbon. There's just not enough money there to be made. What we are looking at is another source of revenue generation that will help growers provide initial seed money for changes in some of the agricultural practices that may come as a result of this, to allow them to upgrade their equipment, allow them to make whatever modifications they wish to do for their agricultural practices, basically to get them over the hump, so that then they can be employing these practices and reducing their carbon emissions, and also promoting the co-benefits, the environmental benefits, the water quality benefits that may come from those type of activities. We have and continue to promote biofuels. We have a segment of our agricultural sector that we believe could benefit significantly from growing of corn, canola, those type of crops that could be turned into biodiesel. Not only will that help promote and expand the agricultural sector, But in looking at some of the data coming out of the Department of Ecology with the whole alternatives fuel or low carbon fuel initiative, biofuels figure quite prominently in reducing the carbon footprint for our largest emitter in the state, and that's private vehicles. Chad talked about the issue of pests. The issue of pests related to climate change is one of much concern to us. We have seen some interesting things over the last couple of years, little flurries, if you will, of pests that we haven't seen in this state that, we've had little blimps and the problem has disappeared, or not disappeared, but has been managed. And it kind of gives us an insight into what we might be expecting in the future. We're also very concerned about this since we are the agency that registers and licenses these agricultural suppressive tools, pesticides. And there is some concern with us regarding new species coming in, species that we haven't seen or species that have been suppressed that all of a sudden burst out because of climate change, and the effectiveness of the agricultural chemicals and tools that we have now. Are we going to be looking at, trying to bring new chemicals on as quickly as possible? Are we going to be looking at maybe, in some circumstances, depending on what the impact may be, going and talking with the US EPA and possibly bringing back some of these older chemicals because of their efficiency for a short duration of time to deal with some of these outbreaks that we may be seeing. Early warning and detection systems, this is something we had talked about back in 2007. I think right now the USDA and us have a pretty good detection system, but faced with the moving northward of some of these pests, both insects and plants, there is some looking at if in fact our current systems that we have in place are sufficient to deal with some of our future issues. And then, again, from an agency standpoint and a policy standpoint, working with WSU, supporting the work that WSU is doing, and some of the land-grant universities, on looking at possibly the development from a genetic standpoint of some of the more pest-resistant crops, based on what we may think is going to be entering the state in the future. So, from a policy standpoint, what we're really looking at is figuring out where we can achieve the balance. From a standpoint of water, we want to make sure that agriculture has enough water to continue to be viable in the state. However, we also realize that we are just part of the pie. Yes, we're a big part of the pie, but we are part of the pie. And looking at where we can strike that balance so that there is sufficient water for everybody in the state to have access to, based on what we may be seeing from climate change. Maybe be a little parochial here, but agriculture we feel must be preserved in the state. It's a huge economic driver. I think it's going to be even more so in the future. And if we were to lose agriculture from the state, we would lose a huge foundation for not only the state, but the economy, but basically for our quality of life. From a mitigation standpoint and policy positions, we feel that agriculture is not well understood yet, but certainly there's more data coming out that, in fact, maybe agriculture isn't necessarily as bad as far as a contributor to CO2 as has been portrayed. However, we really want to refine that and figure out where our baseline is as far as CO2 emissions are, and look at various opportunities that we can to improve agriculture's contribution to not only CO2 emissions, but also providing as much of a sink to atmospheric carbon dioxide as possible.
So we can open, yeah, thank you, Kirk.
We can open it up for questions now.
I have a question just to follow up on your presentation. I think your end point is right to start. The economics of agriculture. We all know there are major distortions, major subsidies. And I think part of where we're going to see pressure in the future is to maybe rationalize. So I'm thinking that we're also going to see pressure for some of these crops that are highly subsidized to maybe be less subsidized because financially we will not be able to afford to provide those corporate subsidies. So I put that in the mix. I'm sure there's going to be pressure globally for providing food sources, but if you look at the water cost, the environmental cost, if you will, as a limiting factor, the crop ability to be grown, and the agricultural subsidy financially on top of that, I'm thinking we may be looking at some more major shifts in the agricultural economy. What do you think of that?
Let me respond quickly to that, and I'll throw it to the policy guy. I think you have to be. Okay, I think you have to be a little cautious in applying the general principle of agricultural subsidization as it is nationally to our state. Because if you look at where the water problems that we've talked about, a lot of these things, that particular segment of agriculture is not subsidized. So our specialty crop industry, our big irrigation-driven system is not program crop. You know, that's the dry land. And so you gotta kind of say, you know, if the issues we're worried about are water use and those kinds of things, those particular farms really don't have that historical underpinning of federal subsidization. Now, there's little things, but it's not like they're getting, you know, paid per acre or that kind of thing. That's program crops, and our only real program crop in the state is wheat, which is not really an irrigated. We do grow wheat under irrigation, but we grow wheat as a rotational crop, and generally it's not a program crop when it's irrigated. So it's just a distinction that I think needs to be made.
And I would add to that is that, I think the understanding of Washington agriculture sometimes gets folded into the program crops that you see in the Midwest. We and as Chad stated right up at the beginning, we are a very heterogeneous state that has contributed mightily to our heavy reliance on minor crops and specialty crops. So it's kind of hard to transfer, it's very hard to transfer nationally issues of subsidies and things like that for what may be happening in Iowa or Nebraska to Washington. It's a different animal, and you know, sometimes that's good for us, sometimes that's not so good for us.
But your fundamental point that the changes will come down the line is certainly the case. But how much those would change our particular situations is not as clear.
A couple of questions. One, just kind of a clarification. Second. Is livestock industry part of agriculture?
Yes. Yeah.
So it would be not much money in livestock, but if part of it, as things dry out, water becomes limiting, that might fill in some gap. The wind farm generation on agricultural land, is that part of the mix? And looking at biofuel production, food production, mixed crops, a wind farm, is that part of your purview, or is that a different story?
We really haven't done any research on wind farms, and in my interactions with our expertise on wind, most of our farmland in this state is really not good wind land, and it's just, it doesn't. I heard this from a guy just the other day. We don't sustain that kind of minimum threshold of wind to justify it economically on most of our farmland locations. The first question is, yes, livestock is huge. Dairy industry is one of our top 5. Even the beef industry is fairly significant. We haven't done a whole lot in terms of analysis on that because the funding that we've had has not said we should do that. And it's just the nature of how we've been funded to do work. There is a planning group currently coming together around kind of Western livestock and climate change that will be submitting a proposal to USDA next year.
I'll chime in here. Most of the wind farm installations you see in the state, like Chad said, aren't really on agricultural land. They're land that, quite honestly, is not all that suitable for agriculture. Specifically, you're not going to be growing much on the ridge tops around Ellensburg. There are down in the southeast corner of the state, there are wind farms that are going in on productive agricultural lands. The contracts that are being negotiated, they're being negotiated individually with the growers. Most of the growers that I have talked to definitely see this as really good supplemental income for them. And at this point in time, there does not seem to be a major conflict with the installation of wind farms on productive agricultural lands. Now, whether that will materialize in the future as these things begin to proliferate or not, I don't know. But right now, there seems to be an opportunity for happy coexistence there. On the livestock issue, we have been doing, I wouldn't say a great amount of work, but certainly work in relationship to greenhouse gas emissions and working with ecology in looking at just what is the percentage of emissions from the livestock industry as opposed to the other half of agriculture. And yes, there are 2 of them. And right now, there's a lot of opportunity to make modifications in things like feed sources, herd management, that look like there would be some opportunities for some reduction or modification into the carbon equivalents that are mitigated. But both the industry, us, and ecology are doing some low-level work on that issue, and we seem to be making a little bit of progress.
We've done a lot of research on manure management options, anaerobic digestion, those things. I didn't really cover that today, but so that we actually, we're a global leader in this region in terms of research on that. We're just starting to see changes in terms of technology adoption. That's an option too. But the hundreds of, or the millions of acres of rangeland, we just haven't even touched that yet.
We have time for, we'll take both of your questions, and they have said that they'd stay, we're just trying to be mindful of time, until 12:30. So if you want, we can have less formal discussions after these 2 questions.
You talk about adaptation, and in terms of, say, plant variety and maybe disease resistance or pest resistance. My question has to do with GMOs, and is that the answer? Is that the only answer? Is there room for a growing, more natural approach to adaptation, or is GMOs the only answer?
being recorded, right?
You notice I didn't jump in there.
It's certainly one of the proposed options, but I don't think it's exclusive. I think the variety of strategies that are currently in use are already being used to adapt to changes in climate-driven factors. At this point in time, the market says no. Whether it will in 5 or 10 years, none of us really know. The one thing I would say from a research standpoint is that whole suite of technologies gives a whole lot more ability to understand the mechanisms by which plants can actually be adapted or adapt. And there's potentially value in using those types of tools just in a research standpoint to say what exactly is going on here, and then taking a different approach to actually getting a plant to do that in terms of commercial application.
And I might add one thing here too, is it was a statement I usually like to make right up at the beginning, is that as far as agriculture is concerned and preparation and adaptation, agriculture has been doing preparation and adaptation since day one. That's basically what it's all about. So at this point in time, when we're looking at dealing with the effects of climate change, in some ways, agriculture has a much bigger table to look at as far as actions to address that than maybe some of the other sectors, just by the fact that, looking at new plant varieties, looking at, changes in irrigation efficiencies, all those sort of things that are on the board or on the table, and looking at adaptation, we've been doing to some extent. It's just a matter of now packaging them up in a cohesive way and moving forward with plans. So in some respects, we're in pretty good shape. Is this going to be a challenge? Yes, absolutely. But I think we're pretty prepared to take on that challenge.
Last question, and then we will unofficially break if you want to stay. But as I said, for more discussion, please feel free. And as you leave, don't forget to stop by the Thurston Energy table that is out there to follow up on our footprint reduction discussion we had a couple days ago. So, question?
Kirk, you were talking about the emissions from the livestock industry. Could you be more specific about the food sources that you were thinking that could help?
Well, right now, and you jump in here as you feel necessary, there has been a lot of research as of late regarding varying the grains and the type of foodstuffs that are supplied to dairy cows and to beef cows, and what the result of methane emissions from the animal itself, as the foodstuffs are easier to digest, cause less methane to be formed, those sort of things. So there is work being done in that, and I think there's a lot of consideration being given to that being one method that could bear some fruit as far as reducing overall emissions from the animal itself. It doesn't really bear a whole lot of impact. Check me if I'm wrong. On the waste and the processing of the manure and stuff like that is basically emissions from the animal itself.
But I'll try and be as quick as I can and as succinct as I can on this. Ruminant livestock are the issue. Manure from any type of animal will create methane if it's in an anaerobic environment. But the ruminants themselves produce methane through enteric fermentation. The rumen in the stomach, basically their waste product is methane. If you look at a cow, the cow has 4 stomachs. The rumen have evolved to take a low quality forage, grass, and convert it into high quality proteins. we know that we can take a high-quality carbohydrate, corn, stick it in that cow, and more efficiently create that protein. And the efficiently there can be described in weight gains, all these things, and also reduces in the amount of methane from enteric fermentation. There's some trade-offs there, though, that aren't really well understood yet. That is, when we grow grass, you can grow grass in a system where you don't have a lot of nutrient input, which has its own emissions factors. You are in a perennial system where you have some carbon sequestration benefits. When you grow corn, all of those additional factors of emissions and production, distribution, and transportation of corn have to be considered in there. So the studies have pretty much focused on that animal unit. Can we feed something differently and gain an efficiency and reduce enteric fermentation? But they haven't looked at this whole picture yet, and it just hasn't been done. So it's a matter of somebody's got to sit down and figure it out, and it's going to be expensive to figure it out. So it's a big uncertainty.
Well, I want to have us give Kirk and Chad a round of applause.